Example 12.1. In the Rutherford's nuclear model of the atom, the nucleus, radius about 10 raised to minus 15 meter, is analogous to the Sun, about which the electron move in orbit having radius 10 raised to minus 10 meter like the Earth orbit around the Sun. If the dimensions of the solar system had the same proportions as those of the atom, would the Earth be closer to or farther away from the Sun than actually it is? The radius of Earth's orbit is about 1.5 into 10 raised to 11 meter. The radius of Sun is taken as 7 into 10 raised to 8 meter. Okay. તો આ જે એક્ઝામ્પલ છે ને એનાથી આપણને જજમેન્ટ આવશે કે આપણે સોલર સિસ્ટમ જે છે એમાં અર્થ ઇઝ રિવોલ્વિંગ રાઉન્ડ ધ સન, રાઈટ? નાઉ ઇફ વી થિંક અબાઉટ the dimensions of earth sun as well as the dimensions of atom and nucleus. Okay, so here we can understand this thing with the help of this example. The empty space, whether it is more in planetary system or in atom, that you can understand. See, radius of the sun, that is 7 into 10 raised to 8 meter, and orbital radius of earth, that is 1.5 into 10 raised to 11 meter. Okay, now radius of atom, that is 10 raised to minus 10 meter, and radius of nucleus, that is 10 raised to minus 15 meter. Okay, so radius of atom give you the orbit of electron, and radius of nucleus, that is the radius of the center. Similarly, radius of sun, that is the radius of the center, and orbital radius of the earth. Okay, that is given to you. So if we take the ratio radius of atom to radius of nucleus, then here we can observe this thing, 10 raised to minus 10 upon 10 raised to minus 15, that is equal to 10 raised to 5, means the radius of the atom, that is 10 raised to 5 times more than that of nucleus. But in case of sun and orbital radius of earth, here we can observe this thing, this ratio that will be of the order of 10 raised to 3. Okay, so now here see, if we take the radius of the sun 7 into 10 raised to 8, now if we multiply this one by 10 raised to 5, then our answer comes to 7 into 10 raised to 13 meter. It implies that at present the orbital radius, that is 1.5 into 10 raised to 11 meter. તો જો આપણે એટમ અને ન્યુક્લિયસ જે છે એના ડાયમેન્શન્સ આપણી પ્લેનેટરી સિસ્ટમ લેવલના ડાયમેન્શન્સ ઇમેજિન કરી લઈએ, તો પછી અર્થની ઓર્બિટલ રેડિયસ જે અત્યારે છે 10 raised to 11 મીટરના ઓર્ડરની, એના બદલે 10 raised to 13 મીટરના ઓર્ડરની હોવી જોઈએ. તો એનો મતલબ કે ઓર્બિટલ રેડિયસ અત્યારે 100 times સ્મોલર છે. ઓકે, તો એનો મીનિંગ એ થયો કે અર્થ સન એનું જો આપણે કન્સિડરેશન લઈએ તો અર્થ અને સનની વચ્ચે જે એમ્પ્ટી સ્પેસ છે ને એની કમ્પેરિઝનમાં ન્યુક્લિયસ અને ઓર્બિટમાં ફરતા ઇલેક્ટ્રોન વચ્ચેની જે એમ્પ્ટી સ્પેસ છે ને એ વધારે છે. પડી સમજ હવે બધાને? ક્લિયર ટુ ઓલ ઓફ યુ? Now, example 11.2. In a Geiger-Marsden experiment, what is the distance of closest approach to the nucleus of a 7.7 MeV alpha particle before it comes momentarily to rest and reverse its direction? Now see, energy of bombarded alpha particle, that is 7.7 MeV, million electron volt. It is in motion, means this energy that is in the form of kinetic energy. Alpha particle is a charged particle. When it penetrates to the atom and reaches very close to the nucleus, so it will experience the repulsive force. As it move closer and closer, closer and closer to the center of the atom, the repulsive force will be continuously increasing one. So, at a particular closest distance from the center of the atom, means from the nucleus, momentarily it will be steady and then rebound. So, when momentarily it becomes steady, so we can say at that time, the total kinetic energy of alpha particle is now converted into potential energy of the system of two charges. One charge, that is charge of alpha particle, another charge, that is the charge of nucleus. So we can write here, at closest distance of approach, the kinetic energy of alpha particle, that is converted into potential energy of the system. So kinetic energy, that is equal to K Q1 Q2 upon R, because it is converted into potential energy, and potential energy of a system of two charges Q1 and Q2 separated by distance R, that is given by K Q1 Q2 upon R. This we studied in second chapter. Clear?
Yes, sir. Sir.
Now, charge Q1, that is the charge of alpha particle, 2e. Charge Q2, that is the charge of nucleus, Ze. And suppose this particular distance of closest approach, that is d, then our equation turns to K2e Ze by d. Now, kinetic energy of the alpha particle, that is given to you, 7.7 m. So 10 raised to 6 eV to joule, multiply by 1.6 into 10 raised to minus 19, that is equal to K 9 into 10 raised to 9 to E and E square. So 1.6 into 10 raised to minus 19 square. In Geiger-Marsden experiment, here we use the atom of gold, and for that Z, that is 79. Okay. Now we have to calculate this D. So make D as a subject. You will get the answer 30 into 10 raised to minus 15 meter. So you can write that is nearly equal to 30 Fermi. Clear to all of you? Now next topic, that is electron orbit. Say Rutherford suggested this thing in atom entire positive charge as well as almost entire mass is concentrated in the small tiny region at the center of it, which is known as nucleus. An electron revolves around it. And he suggested this thing, electron can revolve in any orbit as per the energy possessed by it. We know this thing in different orbit. The energy of electron, that is different one, are also known as energy states or energy levels. Okay. So now when electron is revolving in the orbit, then to sustain its circular motion, centripetal force is required, we know. Now the Coulombian force between electron, which is negatively charged particle, and the nucleus, which one is positively charged. So Coulombian attractive force will provide the required centripetal force. Now, here if we consider the case of hydrogen atom, which one is the simplest type of atom? So for that, there is one proton in a nucleus and one electron is revolving around it. So Z, atomic number, that is 1. Okay. So here we can write the Coulombian force between proton and electron, that is 1 upon 4 pi epsilon 0 E square upon R square, where R, that is the radius of the orbit of electron, means the distance between proton and electron. And that particular Coulombian attractive force will provide the required centripetal force mv square by r, where m, that is the mass of electron, v, that is its orbital speed, and r, that is the radius of the orbit. If we consider any other, suppose we take helium, then for that here we have to use 2e, okay, like that. Now mv square, that is equal to 1 upon 4 pi epsilon 0 E square by r. 1 r is cancelled from both the sides. So if we make r as a subject, then r equal to 1 upon 4 pi epsilon 0 E square upon mv square. This is the equation for the radius of orbit of electron. Then if we make v square as a subject here, take mass on right hand side. So v square, that is equal to 1 upon 4 pi epsilon 0 E square upon mr. Then take square root. So v equal to under root 1 upon 4 pi epsilon 0 E square upon mr. So this is the equation for the orbital speed of electron. Now, energy of electron in the orbit. So total energy of the electron, that is kinetic energy plus potential energy. Kinetic energy, that is half mv square, and potential energy, that is k q1 q2 upon r. So q1, that is charge of proton e, q2, that is charge of electron minus e. So we can write the potential energy, that is minus 1 upon 4 pi epsilon 0 E square by r. Now, here from this particular equation, this one, we can write mv square, that is equal to 1 upon 4 pi epsilon 0 E square by r. So this mv square is replaced by 1 upon 4 pi epsilon 0 E square by r. Now, this one is 1 upon 8 pi epsilon 0 E square by r minus 1 upon 4 pi epsilon 0 E square by r. Resultantly, we will get this total energy, that is minus 1 upon 8 pi epsilon 0 E square by r. Clear? See, the total energy of electron in the orbit, that is negative 1. So when total energy is negative, we know this thing, it is called binding energy. It implies that electron is bounded in the orbit with this much energy. Clear to all of you? Then after, example 12.3, okay? It is found experimentally that 13.6 electron volt energy is required to separate a hydrogen atom into a proton and an electron. Compute the orbital radius and the velocity of the electron in a hydrogen atom. Now see here. The required energy, that is 13.6 electron volt, it implies that electron is bounded with this much energy. So to separate it, we have to provide this much energy. So energy of the electron, that is minus 13.6 electron volt. So that is minus 13.6 into 1.6 into 10 raised to minus 19 joule. Now we have the equation of energy E equal to minus 1 upon 8 pi epsilon 0 E square by R. Take R on left hand side, E on right hand side. So R, that is equal to minus 1 upon 8 pi epsilon 0 E square upon E. So minus 1 upon 8 into 3.14 epsilon 0 8.85 10 raised to minus 12. Then this E square 1.6 into 10 raised to minus 19 whole square divided by minus 13.6 into 1.6 into 10 raised to minus 19. Then solve this one. You will get the radius of the orbit. Then we have the equation for orbital speed. V, that is equal to 1 upon 4 pi epsilon 0 E square upon m E R raised to 1 by 2. Now here substitute the values of E, epsilon 0, mass of electron, and then the value of radius, which one is calculated here. Substitute it in this equation and then solve. You will get the orbital speed of electron. Clear to all of you? See, when any gas or vapor, or we can say which one is at very low pressure. In gas tube, if it is excited, means suppose the electric discharge is passed through it, or we can say by passing the electric current through it. If it is excited, then it emits some radiations having different wavelength. So this particular radiations of different wavelengths emitted by the atom, that is called its atomic spectra. That is called its atomic spectra. Okay. And very first, this type of atomic spectra was obtained by scientist Balmer for hydrogen atom in visible range. So he observed this thing in this particular atomic spectra. Which one was line spectra? Which one was line spectra? Are you clear about the continuous spectra and line spectra? Yes or no?
Yes, sir.
Yes, sir.
Good. Now this particular line spectra, that is called emission spectra. Suppose for the same one, if it is kept at a lower temperature and if the white light is passed through it, then in the spectrum of white light, you will get the black lines exactly at the same positions of the emission spectra. So this type of spectra obtained, that is called absorption spectra. But here, one important thing that we can observe, that is discrete wavelengths are there. This is the line spectra. And here we can observe a specific pattern in this particular spectra. So as the wavelength decreases, the separation between the wavelengths also, or spectral lines, decreasing one. Okay. And Balmer experimentally represented this thing for these particular spectral lines. All the wavelengths can be calculated with the help of one common equation. So a set of all the wavelengths or spectral lines whose wavelengths can be calculated with the help of a common equation. That is called spectral series. That is called spectral series. And this particular specific spectral series for hydrogen in visible range, which one was first obtained by Balmer, and therefore this series that is called Balmer series. And all the wavelengths of Balmer series can be calculated with the help of equation 1 upon lambda equal to R into 1 upon 2 square minus 1 upon n square, where n that is 3, 4, 5, 6 and so on. Now here R that is the Rydberg constant. Its value that is 1.097 into 10 raised to 7 meter inverse. Now here when you substitute n equal to 3 and when for n equal to 3 we calculate the wavelength, then that is called the wavelength of alpha line. Means first line that is called alpha line, second one is beta, third one is gamma, fourth one is delta, like that. And this is of hydrogen. Therefore, when here you substitute n equal to 3, then the wavelength obtained that is called wavelength of H alpha line of Balmer series. Then when you substitute here 4, then it is called the wavelength of H beta line of Balmer series. Like that. So all these experimental observations were obtained. Clear up to this one? First thing. Okay. So after Balmer, so many scientists worked in that particular direction to study the atomic spectra. So scientist Lyman obtained one series in ultraviolet region. Balmer series was in visible region. So all the spectral lines of Lyman series can be calculated with the help of the common equation 1 upon lambda equal to R into 1 upon 1 square minus 1 upon n square, where n equal to 2, 3, 4 and so on. Now here if we substitute n equal to 2, then we will get very first line of the Lyman series. First line is always termed as alpha line. This is for hydrogen atom. So we can say when here we substitute n equal to 2, we get the wavelength of H alpha line of Lyman series. Then if we substitute n equal to 3, then we will get the wavelength of H beta line of Lyman series. Like that. Then after, different scientists obtained different spectral series. This next one, Balmer, we already discussed. Paschen series. So for Paschen series, all the wavelengths obtained in that particular spectral series can be calculated with the help of common equation 1 upon lambda equal to R into 1 upon 3 square minus 1 upon n square, where n equal to 4, 5, 6, 7 and so on. And Paschen series was obtained in near infrared region. So in this equation, if we substitute n equal to 4, then we will get H alpha line of Paschen series. Like that, bracket series, that is in infrared region. For that, the common equation of the wavelengths of spectral lines 1 upon lambda equal to R 1 upon 4 square minus 1 upon n square, where n equal to 5, 6, 7. Then fund series. For that, the common equation for the wavelength of spectral lines 1 upon lambda, that is R into 1 upon 5 square minus 1 upon n square, where n equal to 6, 7, 8, and this one is obtained in far infrared region. So we can write the common equation for all the spectral series like 1 upon lambda equal to R into 1 upon m square minus 1 upon n square. We can calculate the frequency f equal to c by lambda. So equation of the frequency will be RC into 1 upon m square minus 1 upon n square. And here we have to put one condition, m is less than n. So if you take m equal to 1, then it should be less than n. So n that we have to consider 2, 3, 4, then we will get Lyman series. If you take m equal to 2, then n will be 3, 4, 5, you will get Balmer series. Then after, if you take m equal to 3, then n will be greater than m always. So 4, 5, 6 onwards, we will get Paschen series. So in this way, we can prepare a common equation to calculate the wavelength of any spectral line of any spectral series. Clear to all of you? Now see, experimentally we obtain the line spectra. Okay, atomic spectra, that is the line spectra. Now if we think about Rutherford's atomic model, Rutherford suggested this thing: electron revolves around the nucleus in different orbit depending on the energy possessed by it. Okay. Now, if electron is revolving, it implies that its motion, that is accelerated one. Centripetal acceleration will be there. And as per classical electrodynamics, if any charged particle is executing accelerated motion, then it emits the energy in the form of radiations. Okay, so now if electron is revolving, it emits the energy, then its energy will be continuously decreasing. It implies that it will move closer and closer to the nucleus. So its motion will be not circular one, but that will be spiral one. And after some time, the motion will be end up at the nucleus. એટલે છેલ્લે ન્યુક્લિયસમાં જઈને બેસી જશે. Okay? So, if this happens, then what about the stability of the atom? And if the motion of the electron is a spiral one, its energy is continuously decreasing one. There is no break in it. Then there should be the continuous atomic spectra. But here we are getting line spectra. It implies that now Rutherford atomic model was failed to explain these experimental observations. So we can say, no doubt, Rutherford's atomic model is partially successful. He suggested almost entire mass is concentrated at the center in the nucleus, and entire positive charge is also concentrated in the nucleus. Electrons are revolving around it. But why line spectra is obtained? Why not continuous one? Okay, and what about the stability of atom? So all these things were not able to explain. So at this stage, Rutherford's atomic model was failed. So scientist Bohr studied all these things, right? He studied Rutherford's atomic model, his experimental observations, as well as he studied all these atomic spectra, and then after he represented the atomic model, which one is known as Bohr model, which one is based on postulates.
સર આકાશનું ચાલુ છે.
So Bohr's atomic model is based on postulates, and in that he combined classical electrodynamics and newly developed the concept of quantum mechanics. That concept of quanta of energy, photon, which we studied in chapter 11, dual nature of matter and radiation, right? In that we studied that particular concept. So Bohr combined these two and he represented the atomic model. But he represented this atomic model in the form of postulates. So now we have to discuss the Bohr atomic model and up to what extent it can explain the actual atomic structure that we have to discuss. Clear to all of you? According to the classical electrodynamic theory, calculate the initial frequency of the light emitted by the electron revolving around a proton in hydrogen atom. Okay. So in previous example 12.3, we calculated the radius of the orbit of electron and its orbital speed. Radius comes to 5.3 into 10 raised to minus 11 meter, and orbital speed, that is 2.2 into 10 raised to minus 6 meter per second. Now orbital speed, that is distance upon time. So when one revolution is completed by electron, the distance covered, that is the circumference of the orbit, 2 pi r. Time taken to complete one revolution, that is the periodic time, t. So we can write 1 upon t, that is v by 2 pi r. But reciprocal of periodic time, that is the frequency. So frequency f equal to v upon 2 pi r. Now substitute the value of v, 2.2 into 10 raised to minus 6 upon 2 pi 3.14 r, 5.3 into 10 raised to minus 11. Then solve it. You will get the frequency of the electron. Okay, clear?